Okay, here's the rest of the acid-base review for the midterm. Um, Real quick look at the acid-base properties of salts. Salts, of course, are compounds where you have a positive ion, the cation, combined with the negative ion, the anion. You might recall from Chem 1, they probably beat this into your brain. An acid plus a base react to produce a salt and water. So, how do you tell if a salt is acidic, basic, or neutral? One way to do it is to try and picture the acid-base reaction that produced the salt. Any salt can be pictured as coming from an acid and a base. So, let's say you took the strong acid, hydrochloric acid. In this analysis, SA stands for strong acid, strong base, weak base. You get the picture. So if you take hydrochloric acid and react it with a strong base, sodium hydroxide, they will react, and you're going to end up making water, of course. Where's the water come from? The hydroxide in that. Hey, the leftovers, the things that don't turn into the water, turn into the salt. So your salt is sodium chloride. If you took the strong acid, nitric acid, HNO3, and say reacted it with potassium hydroxide, that's a good strong base, you're going to end up making water, and the salt is going to be potassium nitrate. Here's the rule. Strong acid plus a strong base, it's kind of like the two strong things cancel out, and you get a neutral salt. If you put sodium chloride into water, it will not affect the pH. It is a neutral salt. No effect on the pH whatsoever. Potassium nitrate. Drop a whole bunch of that in water. Is it going to make the pH go up or down? Nope, not one bit, because it's a neutral salt. Now, what if you took a strong acid and reacted it with a weak base? Say we go back to our hydrochloric acid here, and we put it together with ammonia. Remember, ammonia is a weak base. They're going to react. Turns out you don't even get water in this reaction, but heat transfers his proton over here, and you're going to get this salt, NH4Cl, ammonium chloride, which is essentially an ammonium ion combined with a chloride ion. Ammonium chloride is a nice white powdered substance. You sometimes see it form in chemistry stockrooms. If you have the ammonia cabinet close to the cabinet that has hydrochloric acid, the two compounds waft towards each other. When they hit, they form this. It's kind of interesting. If you have a bottle of this, take the lid off. You can't see it, but you'll occasionally catch a whiff of the HCl. Not good. Catch a whiff of this, it's invisible. Where the two clouds hit, it turns all white because it's making this salt. So, strong acid, weak base. Who wins? The stronger one wins. So the salt that is produced is going to be acidic. So ammonium chloride is an acidic salt. Let's say we took the strong acid, hydroiodic acid, and we combined it with, say, an organic amine like methylamine. So this is methylamine. Hey, he's going to transfer a proton over here, and we're going to get methylammonium iodide. It's going to be CH3NH3I, which is really the methylammonium ion combined with the iodide ion. So, strong acid plus a weak base. Again, who wins? The strong guy wins. You get an acidic salt. So if you were to drop some ammonium chloride into water, got a nice neutral beaker full of water, you drop some ammonium chloride in, it's going to dissolve, it's going to split into its individual ions, and the pH is going to go down. That pH is going to go down a little bit because the ammonium ion is slightly acidic. This ammonium ion can transfer a proton to the water. What if you have a weak acid and you react it with a strong base? Then you get a basic salt. Simple example, hydrofluoric acid. He's a weak acid, really dangerous acid. Don't get me wrong, incredibly dangerous stuff, but technically he's weak. He's a weak acid. If you react that with a strong base, let's be different here and pick on lithium hydroxide. He's a good strong base. They're going to react. What are you going to get? Well, you of course make your water. Your salt is going to be lithium fluoride. Hey, that salt is basic. Weak, strong. Who wins? The strong guy. The basic half wins. So it produces a basic salt. If you drop this stuff into water, it's going to dissociate, and it turns out fluoride ion is kind of basic. So it will raise the pH of the solution. Bases will, of course, make the pH go up. Acids make the pH go down. So that's a quick look at acid-base properties of salts. Now, on the midterm, you're going to get a question that's going to look a little bit like this concerning a titration. Thing to know is when you're doing a titration, you end up with a salt. Let's say you were going to do a titration of hydrofluoric acid here. So you have some hydrofluoric acid, and you add sodium hydroxide to it. I start with 1 mole of the acid, and I add half a mole of this. Do I still have a mole of the acid in here? Of course not. The base will destroy some of the acid. So I'll end up with half a mole of the acid, half a mole of the salt, or the conjugate base. If I add another half a mole, now I've completely neutralized my acid. I started with 1 mole of the acid, now I just have 1 mole of the salt, the sodium fluoride. Hey, that sodium fluoride is a basic salt. So I've neutralized the acid. Does that mean the pH is 7? No. Now I've got a solution of a basic salt. The pH is going to be above 7. It's probably going to be closer to 9, 10, something like that. Because again, he is a basic salt. So the brutal sort of question on this sort of thing is what you're seeing here. Let's say you're doing this sort of titration. Sorry, I'm not using hydrofluoric acid in my example. I'm using acetic acid. It's the active ingredient in vinegar. You got the Ka, and it says you start with a 20 milliliter sample of acetic acid. It is titrated with 0.1 molar sodium hydroxide. It takes 30 milliliters to reach the end point. What is the pH of the solution at the end point? Oh God, there's a lot going on here, guys. What you got to see right off the bat is that you're going to make a basic salt. So you're going to start with your acetic acid. Plus your sodium hydroxide. You're going to make this salt. And water, of course. This salt is a basic salt because you're reacting a strong base with a weak acid. How did I know it's a weak acid? Oh, they gave me the Ka value for it, the acid ionization constant. So you know the pH is going to be above 7 because when all is said and done, what you have here is a solution of a basic salt. So it's going to have a pH above 7. If you wanted to know the actual pH, oh boy, okay, how do you deal with that? Well, if you know the molarity of your sodium acetate, and instead of doing I'm going to drop the sodium off here and just do it as C2H3O2 minus 1. That's the acetate ion. That's the part that makes it basic. If you had to know the molarity of this, it would be the moles over liters. Well, how many liters are in that solution? Hey, you took a 20 milliliter sample and you titrated it by adding 30 milliliters. You added a total of 50 milliliters, which is 0.050 liters. So you're going to have 0.050 there. How many moles? How many moles were there? Oh, yeah, titration. You know the molarity of this stuff. You know the volume of it. I could do 30 milliliters times 0.100 mole per 1,000 milliliters. I'm going to get, what does that give me? 0.003. So that many moles of sodium hydroxide were added to reach the endpoint. That means that's how many moles of this I had, and that's also going to be the number of moles of this. So your molarity here on this stuff is going to be your 0.003 moles per 0.050 liters. It's going to be 0.06 molar. So what that's telling us is, when this titration is all said and done, what do I have? I've got a solution of 0.06 molar sodium acetate. And this stuff is a base. I've got a weak base solution. So if it's saying, what's the pH? It's a weak base solution. I got to find the pH of. That's the kind where sometimes you have to make the ice table and all that to solve it. And guess what? If it's a weak base solution, I don't need Ka. I need Kb. So you have to use the old Ka times Kb. Gives you 1 times 10 to the minus 14th. You know the value of Ka. You know this number, you can solve it for Kb. Kb for this compound is going to be your 5.56 10 to the minus 10th. All right, so I got my Kb value. I know it's a weak base problem. I can make an ice table, solve for X. X, of course, represents the hydroxide concentration, and from there I can find the pH. I tend to skip the ice tables. I think I showed you this shortcut earlier. These weak base problems, weak acid problems, you can just set it up as Kb is going to end up being X squared all over the molarity, which in this case is 0.06 minus X, which we say is approximately the same thing as saying X squared over 0.06. And Kb, of course, we have a number. What is that number? 5.56 times 10 to the negative 10th. Hey guys, can you solve this for X? Sure you can. You solve that for X. X here happens to be 5.78 10 to the minus 6. And that happens to be the hydroxide concentration. And then from there you can find the pH at the end of this problem. The pH I ended up with here, 8.76. So at the end of this titration, that's the pH that the solution will have. There's a lot going on in that problem there. But again, expect one like that on the midterm. So guys, that's it for the midterm review on this acid-base stuff. And good luck on the midterm.